This lesson deals with the phasor form of Ohm's law. You can find these notes in the ECE 202 ebook in Chapter 8 starting on page 12. Let's go back to ECE 201 and pick up our definition of a resistance. Had a voltage across it and a current entering the plus terminal leaving the minus terminal because it absorbs power at every instant in time. But now our voltage and current, let's specifically label them as functions of time. Again, this is our time domain equivalent of a resistance. And then by Ohm's law, the voltage V of t is equal to R times the current I of t. But suppose that now is our default definition of our current. In other words, a magnitude of I sub a cosine of omega, t plus V. Bring the R inside here, and we could write this as the real part of R times I of a times e to the j phi times e to the j omega t. This term over here is what we call the phasor voltage. Just label it as V with a bar on top of it. Again, that has to equal now R times I of a e to the j phi, but you can also write this as I sub a at angle phi, but this is also our definition of the phasor I with a bar on top of it. So we could express Ohm's law in the frequency domain with the same symbol R, but a phasor voltage across it and a phasor current entering the plus terminal leaving the minus terminal. Now the phasor voltage has an angle, phasor current has an angle. They're both the same because they're just multiplied by a scalar. You just think of this as really a magnitude at angle 0. So we could sketch a phasor voltage with our real and j imaginary axis, have some length, and the current would be some other length, but it would be at the same angle phi. We sometimes call this being in phase, in that both V of t and I of t have their maximums and minimums at the same instant in time. Let's take a look at an inductance and see what the relationships are for voltage and current for this element. Again, let's go back to ECE 201, and we have a coil with a voltage across it, current entering the plus terminal leaving the minus, and a value of L. Suppose our current again is a cosine function with an amplitude of I sub a, frequency of omega, and angle of phi. As we saw back in chapter 6 of 201, V of t is equal to L di dt. So let's take then and find the voltage in the time domain given this current. Okay, so we've got L. The derivative of cosine is minus sine. So here's the sign of the same argument with the minus sign. And then we're going to take the derivative of what's inside these parentheses with respect to t. That's just going to be omega plus 0. So here's where I get the omega from. Let's rearrange these terms a little bit, put the minus omega in front and the L times I of a. But we're looking at cosine functions, not sine functions. So we got the cosine of omega t plus phi, and then some angle that would make the cosine function equal to sine. I always get confused whether it's the plus or minus 90. The way I reason it out is the following. Set this equal to 0 here, so I got the cosine of minus 90. That's going to take the peak of the cosine function, which would normally occur at t equals 0, and shift it to the right by a quarter cycle. I can visualize that, but that is what a sine wave looks like. Okay, so I've got replacing then the sine by an equivalent cosine shifted by minus 90 degrees. Could write this then as the real part of minus omega L I sub a, and then e to the j of this whole argument here, omega t plus phi minus 90. Let's just break this apart into three summations. So I've got e to the j phi, e to the j minus 90, and then e to the j omega t. So when you apply these three terms, we're going to add their exponents. Get back to this expression here. We know what this is and we know what this is, but what is this? Let's figure it out. So e to the j minus 90, we could use Euler's identity or formula. Take the cosine of minus 90 plus j sine of minus 90. The cosine of plus or minus 90 is 0. Then we have the sine of minus 90, and that turns out to be equal to minus 1. We get a minus j. So you could write this then as V of t is the real part of the quantity. Now I've got a plus j omega L I sub a e to the j phi times e to the j omega t. We're just replacing this term here by minus j. This is our definition of our phasor voltage. This is the term that we're going to suppress and put it back when we go back into the time domain. So let's take a look at this equation and see if we can figure out Ohm's law. Taking this equation back over here, I've got the phasor voltage is equal to j omega L I sub a times e to the j phi. Or you could just write this as just angle phi. But this is our notation for our general phasor current I with a broken arrow on top. So we've got the voltage is equal to j omega L times I. We've got, again, an Ohm's law types relationship, but this is in the frequency domain. But now our resistance is actually an imaginary number. It's j omega L. So the inductance in the frequency domain looks like an imaginary number equal to j omega L. So if you know the current, you can find the voltage by multiplying the current times j omega L. Let's do that over here and just draw a phasor diagram. I have j omega L here, and I could represent that as a magnitude of omega L, and the angle will be 90 degrees. We're in the boundary between the first and second quadrant. You can also punch that in your calculator and get the same result. Let's go back and write I as I sub a at angle phi. The overall magnitude is the product of those two terms. The overall angle is the sum of the two. So if we had a current I sub A at angle phi, let's draw that here as just some arbitrary length with an angle phi, the voltage would be a different length, and the angle would be an additional 90 degrees. So another 90 degrees added to this, and then the length of the term here, omega L times I sub A. It's worth noting that this length changes with frequency. The angle of the current is behind the angle of the voltage by 90 degrees. We say that that lags by 90 degrees. Whenever we refer to these kinds of terms, we'll do the current with respect to the voltage. So the current is lagging the voltage by 90 degrees. Take a look at a capacitance. Again, let's go back to ECE 201. Take our time domain definition, which is the voltage across the capacitance, current entering the plus, leaving the minus, and that the current is equal to C dV dt. Let's let the voltage here be our default, with a magnitude of V sub A, a frequency of omega, and a phase angle of phi. You could also do this with an integral relationship. I just find it easier to differentiate. So I've got C times the derivative of this equation, which is going to be V sub A, of a minus sign of the same argument, and then the derivative of this with respect to t would be equal to omega plus 0. Rearrange the terms here. I've got minus omega c V sub A, and then we're doing cosine functions, so I need to shift this by 90 degrees. So the cosine shifted by minus 90 is the sine, as we talked about on the last page. I could write this as the real part of this term here, minus omega c V sub A, and then e to the argument here of omega t plus phi minus 90. Let's write this as a product of three exponentials. So I'll do j phi first, minus j90, and then I've got a j omega t. We found on the last page that this was equal to minus j, so let's substitute that back in. So the minus j and the minus sign here cancel, and I just get a j, and I get omega c v sub a e to the j phi. This would be our phasor current representation of I of t. So let's pull this off on the side and see if that looks like Ohm's law. So I have I as a phasor, is j omega c v sub a e to the j phi, and again you could write this as just the angle of phi. And of course this is our default definition of a voltage phasor, V with a broken arrow on top. Divide through the other side of the equation, I have 1 over j omega c times the current phasor I. This is, again, is our Ohm's law definition, but in the frequency domain. Let's sketch the phasor diagram of the voltage and current here. Suppose I have a voltage V sub A at angle phi. Let's draw that as some length at angle phi. And I'm going to multiply the voltage, brings on the other side of the equation here, by j omega c, which would be 90 degrees times omega c, magnitude of omega c, again on the border between the first and second quadrant. So the overall angle is the sum of the two, overall magnitude is a product of these two. So given the voltage, you can multiply that magnitude by omega c, get some length, but the angle is 90 degrees more than the angle of the voltage. If we refer to the current with respect to the voltage, the current here is ahead of the voltage by 90 degrees. So we say that it leads the voltage by 90 degrees. We'll always do the current with respect to the voltage. Now, how can you keep all this stuff straight in your head? When I was a student taking this course, the instructor gave me this little memory trick for remembering relationships between voltage and current for the capacitor and the inductor. He said, remember Eli the Iceman. And what he meant by this was that if we take the phasor diagram for inductance, which had our current and voltage in this relationship, the current was lagging behind the voltage. But in physics, we used the letter E for voltage. And actually, in early days of electrical engineering, we did the same thing. And this would spell Eli if you put the L here for the inductance. And then for the capacitance, we had that the current was leading the voltage by 90 degrees. And I put down that this is for a capacitor. And here's my I. And then if I, instead of using V, I use the letter E. I get the combination of letters here to spell ice. My instructor was referring to something that he had as a child, which was an ice delivery man. Early days of refrigeration, they would bring blocks of ice, and you'd put that in your refrigerator and keep your food cold until maybe the next day when they bring another block of ice around. Like many things, just a simple memory trick like this that I learned a long time ago. I still remember it as a quick way to remember the voltage and current relationships for inductance and capacitance. Let's summarize this in a new form of Ohm's law. I'll say that V is equal to Z times I, where Z in the frequency domain is taking the place of R in the time domain. We call Z an impedance and show it as a general rectangle. But if we had a resistor in here, we'll use the resistor symbol, and the value then of Z would just be equal to R. If we had an inductance in the box, we just use the inductance symbol, and the impedance of that was j omega L. And if we had a capacitance in the box, just use the capacitor symbol, and its impedance is 1 over j omega C. We can also do this to the equation. Let's multiply numerator and denominator by j. So I get j over j squared omega c. The j squared is a minus 1, so I get minus j divided by omega c. So I could use this or this as a way to represent the impedance. Now in the time domain, we also had that I is equal to G times V. We'll have something similar in the frequency domain. We'll just say that I is equal to Y times V, and Y will be called admittance. The units on Z are ohms. The units on admittance are mhos or Siemens, just like we did in the time domain. And if we have a resistor in the box, we'll then say its admittance is 1 over R, or just G. If we have an inductance in the box, its impedance was J omega L, so its admittance would be 1 over J omega L, and that would be a minus J over omega L. And if we have a capacitance in the box, we would say its admittance is the reciprocal of its impedance. One last note here, only voltage and current have the broken arrow over the letter V and I. Although there's symbols and numbers, we're not going to use any special designation, but just for voltage and current. And these are some of the properties of the phasor form of Ohm's law.